Electron affinity is defined as the energy that's released when an atom gains an electron. So we said that fluorine, when it gains an electron, it has it does release energy. Now, you can think of electron affinity as really the ionization energy for the ion with a negative 1 charge. Think of it this way. Fluorine gas atom, an atom in the gas phase, plus an electron gives you F minus. The energy associated with that is called, the energy that's released is called the electron affinity. Well, what's the reverse of that process? You have F minus, okay, giving up its electron to give you back the fluorine atom, okay? The energy for this is called the ionization energy of fluoride. So the electron affinity of fluorine is the ionization energy of fluoride. So what would be the trend in electron affinity across a row in your periodic table and down a column? The trend will generally follow those for the ionization energy, because let's take a look at this one. Lithium, the EA of lithium is really the same thing as the ionization energy of lithium with a negative 1 charge, right? And the EA of beryllium is going to be the ionization energy of beryllium with a negative 1 charge. So in effect then, remember, ionization energy increases left to right. We have to stop at the halogens. This time around, it's the halogens that are going to have the highest electron affinity. So electron affinity increases going left to right. Okay. Now there are exceptions. Okay, and exceptions that have completely filled valence subshells will have very low electron affinity. So beryllium, magnesium, calcium, group 2A. S2, okay, because you have a completely filled subshell, because the next electron will go into a higher energy subshell. Those tend to have very low electron affinity. In fact, electron affinities are not really easy to measure, and so they can't be reliably measured for this group because it's very low. Same thing with the noble gases. Okay, they have a very low electron affinity. Let's consider helium. You got 2 electrons on the outermost shell. If you add 1 more electron, okay, it's going to be in a bigger, much bigger shell. That extra electron is going to be so easy to remove. It's not going to stick around. So the electron affinity for helium is going to be very small. So for noble gases, you have very low electron affinity. There's also a unusually low electron affinity. There's a break in the trend for group 5A. Okay, these have a valence configuration of P3. And that's because in a P3 configuration, you have 3 unpaired electrons spread out among the orbitals in the P subshell, and when you have to put the 4th one in, you're going to have more additional repulsions involved, so you're not get as much stability when you put that 4th electron in. Okay. Now there's also so what about going down a column? The trend going down a column will pretty much just follow ionization energy as well. So going down a column, okay, there's going to be, remember, decreasing ionization energy, right? The electron affinity will also be decreasing electron affinity. Now, there is a break, though, in going from row 2 to row number 3. So that trend really starts from row number 3 on down. So this means that chlorine would have a higher electron affinity than bromine. Okay, so going down, you have decreasing electron affinity. Okay, but there's an exception. Instead of going down from fluorine to chlorine, it's actually going to go up. So chlorine, we say, will have a higher ionization electron affinity than fluorine. And the reason for that has to do with the size of the group 2 the second row elements, the atoms in the second row elements. They're so small that that extra electron is going to be going into a much crowded area as far as electrons are concerned. It's going to experience a much stronger electron repulsion. Okay, so you're not going to have as much of an energy release that you might with the atoms in that row.